Section 1, we're going to discuss the differences and similarities between mixtures and pure substances. Mixtures contain two or more pure substances. Mixtures do not obey the law of definite composition. Therefore, the relative amounts of each substance can vary depending on the sample. Let's look at an example of this. A pure substance is something we might consider pure water, H2O. Every molecule of water is 2 hydrogens and 1 oxygen covalently bonded. By mass, the composition is 89% oxygen, 11% hydrogen. And the only way to separate the hydrogens from the oxygen in a water molecule is by chemical means. Contrast that with salt water. It has water in it, but it also has various salt ions, calcium ions, chloride ions, sodium ions. The composition varies by mass. Does it have a lot of those salt ions in there or only a little bit? Like, we don't know what percentage of any given sample is sodium, is chlorine, is water. And we can separate mixtures often by physical means. So salt water can be distilled and purified down to that pure water. That is a physical process. Most mixtures can be separated using physical means, while pure substances will always require a chemical process to separate the elements that make up the compound. There are 3 types of mixtures that we're going to talk about. They are defined and differentiated by the diameter of the particles in the mixture. Suspensions have particles that are greater than 1,000 nanometers, so the largest particle size. In the middle are colloids, which have particles that are between 1 and 1,000 nanometers, and solutions have the smallest particle size, particles that are less than 1 nanometer. Let's go into a little bit more detail now about each one. First, suspensions. Due to their large particle size, the particles in a suspension will not remain suspended indefinitely. Over time, the particles will settle out. Muddy water is a good example of a suspension. The mud in a river will often stay suspended for some time due to the continual movement of water. However, once the water velocity slows, the mud particles will settle to the bottom. Another example of a suspension that you're familiar with from previous studies are the formation of precipitates. When precipitates form from a mixture of 2 aqueous solutions, a suspension is created from the solid precipitate. In the beaker below, you can see as we combine these 2 colorless aqueous liquids, we form this yellow precipitate, okay? And it is a suspension. Eventually, it will settle out down at the bottom of the beaker of the aqueous medium. Let's talk a little more about colloids now. Due to their smaller particle size, remember colloids are in the middle from 1 to 1,000 nanometers, so smaller than suspensions. The particles in a colloid will not settle over time, but they remain suspended indefinitely. Fog is a classic example of a colloid, as the water droplets neither dissolve in the surrounding gaseous medium, nor do they settle out and fall to the ground. You see in the photo these beautiful sun streaks as the light hits the fog in the image. That scattering of light that causes that pretty sun streak, the scattering of light by particles in that colloid in the fog is called the Tyndall Effect. It can be seen when driving through fog as the light from the headlights gets scattered by the particles. It is also seen as the sun shines through the fog in the image. The Tyndall effect can be used to distinguish between colloids and solutions because solutions do not exhibit it. So if you're given 2 examples, one where light is scattered by the particles in the solution, one where light is not. The one where light is scattered would be classified a colloid, and the other might be classified as a solution. Let's talk more now about solutions. Solutions contain the smallest particles, particles that are less than 1 nanometer. In a solution, dissolved particles, known as the solute, are surrounded by solvent particles. The solvent is the medium in which the solute particles are dissolved. So let's think back to our saltwater example from the first slide in this section. If you're dissolving salt in water, the salt is the solute, the water is the solvent, and that mixture overall would be classified as a solution. It is a homogeneous mixture of solute and solvent due to the small size of the solute particles. Solutions can be mixtures of gases, liquids, or solids, as shown in this table of examples. However, we are going to concern ourselves with the properties of liquid solutions, particularly those containing water, for the rest of this presentation. But just as an example, there is a mixture, a solution of air and natural gas. The solution is gas, solute is gas, the solvent is gas. Vodka is a solution of liquids. Brass is a mixture of two solids in solution. Carbonated water is liquid and gas to form a liquid solution. Seawater is liquid and solid to form a liquid solution. And hydrogen gas and platinum metal, gas and solid with an overall solid state of the solution. So these types of solutions can come in many forms and states of matter, but again, we're going to focus mostly on liquid solutions, particularly those containing water. Solutions are always homogeneous mixtures because regardless of sample size, the ratio of solute particles to solvent remains the same. So in this sample of purple solute to green solvent, no matter where you take the sample from, if you took a 5 milliliter sample or a 200 milliliter sample of the solution, you would find the exact same ratio of solute to solvent. Salt water is a classic example of a solution. The sodium ions and chloride ions are dissolved in the solvent, creating a uniform mixture. So you can see three sodium ions and 3 chloride ions, and then a bunch of water molecules here. And it would make sense that the positive ends of the water are near the chloride, the negative ends are near the sodium. Okay, most water that we encounter in our day-to-day lives is a mixture. Water from the tap or freshwater sources are not completely pure. Minerals from rocks and soil dissolve in the water. However, in such small proportions, that is not considered salt water. This scary looking fella is a saltwater crocodile, and in order to survive, he needs a mixture of water and several solutes. He can't survive in fresh water. So salt water has a much greater amount of solute than fresh water. So fresh water, what we would think of coming from our tap or from freshwater lakes, rivers, streams, it does have some solutes dissolved in it, but not nearly in the concentrations that we would find in saltwater bodies of water, to the point that some sea creatures and saltwater creatures can't survive in fresh water because they need that high concentration of different solutes in the water. All right, here's a summary of those 3 types of mixtures that we talked about. Remember that we differentiate them based on their particle size. So suspensions greater than 1,000 nanometers, so the largest particle size. Colloids in the middle, 1,000 down to 1 nanometer. And then solutions have the smallest particles, less than 1 nanometer. The only ones where the particles will settle are in a suspension. Both colloids and solutions are homogeneous. And again, that's because the particles aren't settling out. Colloids and suspensions both exhibit the Tyndall effect, but solutions do not. So even though a colloid and a solution are both homogeneous, where you can't see the particles separate from the solute, separate from the solvent, only the colloid will exhibit the Tyndall effect. And how do we separate these types of mixtures through physical means? Suspensions, because they're large particle size, can just be separated by filtration. You can think of like a coffee filter type of filtration. We have other kinds of filters in the lab, but it's as simple as filtration. Colloids and suspensions have to be separated through a little more intensive measures, things like distillation to purify out the solutes and evaporation. We had talked about how in this course we're going to focus primarily on solutions involving liquids, but a mixture can consist of only solids. One example is concrete, which is a mixture of cement, a powdery substance, sand, rock, and gravel. In this case, the different components of the mixture are not evenly distributed. They're clumpy, right? When you see concrete, you can see different pieces of the mixture throughout. This is what we would call a heterogeneous mixture of solids. Let's contrast that with another example that is a mixture of solids, alloys. Alloys consist of a mixture of metals and sometimes other elements. For example, bronze is a mixture of copper with other metals such as tin, aluminum, manganese, nickel, or zinc. In this case, the different components are evenly distributed throughout. They are not clumpy. This is a homogeneous mixture of solids.